Welcome to Chapter 9 entitled Estimating the Value of a Parameter. Section 9.1 Estimating a Population Proportion. So, inferential statistics is the process of using information from a sample to make conclusions about an entire population. Estimation is when we use sample data to estimate the value of an unknown population parameters such as P, which is the population proportion, mu, which is the population mean, and sigma, which is the population standard deviation. Why do we need this? Well, we cannot survey everyone in a population because it could be too expensive, too time consuming, sometimes impossible. So we take a sample and we use it to make educated guesses about the whole population. So consider a population in which each member either has or does not have a specified attribute or characteristics. For example, we might want to know what proportion of Americans support a particular policy or what proportion of students pass an exam. Then we use the following notation and terminology. The population proportion P is the proportion or percentage of the entire population that has the specified attribute. So this is what we want to know, but usually cannot measure directly. An example would be the true proportion of all American adults who worry about their finances. Sample proportion, read as P hat, is the proportion or percentage of a sample from the population that has a specified attribute. It's computed by using the formula P hat equals X divided by N, where X represents the number of individuals in the sample with the specified characteristic, and N is the sample size. Think of it like this. If you survey 100 people and 60 say yes, then P hat would be 60 divided by 100 or 0.6 or 60%. So let's do an example. In a survey of 2019 adult Americans aged 18 years or older, 1,252 stated that they frequently worry about their financial situation. A is asking us to determine the number of observations N and number of successes X. So N would be the 2019 adult Americans. That's the number of people that were surveyed. And then X would be the 1,252 that stated that they frequently worry about their financial situation. So for B, we now want to find the sample proportion of adult Americans aged 18 years or older who frequently worry about their financial situation, round proportions to 3 decimal places. So to find our proportion, we are going to take X divided by N, which then gives us the decimal 0.620. Objective 1. Obtain a point estimate for the population proportion. So, what is a point estimate? We got to start there. So, suppose we want to estimate the proportion of adult Americans who believe that the amount they pay in federal income taxes is too high. It is unreasonable to expect that we could survey every adult American. Instead, we use a sample of adult Americans to arrive at an estimate of the proportion. We call this estimate a point estimate. So a point estimate is the value of a statistic that estimates the value of a parameter. It's our best single guess based on sample data. Some examples of point estimates are X bar is a point estimate for mu. So the sample mean estimates the population mean. We have p hat is a point estimate for p. So the sample proportion estimates the population proportion. We have S is a point estimate for sigma. So the sample standard deviation estimates the population standard deviation. And S squared variance estimates the population variance. So an important note is that a point estimate is just a number. Okay, it's our best guess. But how confident we are in that guess, that is where confidence intervals come into play. All right, objective 2, construct and interpret a confidence interval for the population proportion. Okay, so why do we need confidence intervals? So a better way to estimate population parameters is by creating a range of values called a confidence interval. In statistics, we construct an interval for a population parameter based upon a guess along with a level of confidence. The guess is the point estimate of the population parameter, and the level of confidence plays a role in the width of the interval. Think of it like this. Instead of saying, let's say, exactly 62% of Americans worry about finances, we would say we are 95% confident that between 60 and 64% of Americans worry about finances. This gives us a range that probably contains the true value. So then what is the confidence interval? Well, the confidence interval is a range of is a range or interval of values used to estimate the value of an unknown parameter. The confidence interval is a way to estimate a population parameter by creating a range of values that is likely to contain the true population parameter. Mathematically, it is where the parameter is greater than your lower bound, but less than your upper bound, or it's written as lower bound, comma, upper bound. Okay, right here. Note that p hat forms the basis of the interval, and the margin of error is subtracted from it and then added to it. So the margin of error here is labeled as capital E. So it can also be written as p hat minus E and then p hat plus E, or p hat plus or minus E, or written as an ordered pair. All right, so the level of confidence or confidence level represents the expected proportion of intervals that will contain the parameter if a large number of different samples is obtained. The level of confidence is denoted as the quantity 1 minus alpha times 100%. The confidence level is sometimes explained as the success rate of the procedure. But what does this mean in plain English? Well, let's say, for example, a 95% level of confidence, which is where alpha equals 0.05, implies that if 100 different confidence intervals are constructed, each based on a different sample from the same size, from the same population, then we can expect 95 of the intervals to include the parameter and 5 not to include the parameter. In other words, the method is correct 95% of the time. So an important distinction here is that we are not saying that there is a 95% chance the true parameter is in our specific interval. We're saying that if we repeated this process 100 times, about 95 of those intervals would contain the true parameter. All right. So to understand how to construct a confidence interval, we need to know about the model that describes the sampling distribution of p hat, the sample proportion. Okay. First, the shape of the distribution of all possible sample proportions is approximately normal, provided that n times p times 1 minus p is greater than or equal to 10. The sample size is no more than 5% of the population size, and the data are obtained randomly. So this means that when our sample is large enough and random, the sample proportions from repeated samples will follow a bell curve, which is a normal distribution. The second thing to consider is that the mean of the distribution of the sample proportion equals the population proportion. That is mu sub p hat equals p. Translation: on average, our sample proportion equals the true population proportion. Sample proportions, remember, target the population proportion. And the third thing to understand is that the standard deviation of the distribution of the sample proportion, the standard error, is sigma sub p hat, which equals the square root of p times 1 minus p divided by n. So this tells us how much sample proportions typically vary from sample to sample. So larger samples will have a smaller standard error or less variability. Okay. Now, it's critical that we understand what confidence level means before we move forward into some practice problems. So the level of confidence refers to the confidence in the method, not the specific interval. So the most common confidence levels are 90%, 95%, and 99%. Again, we can always write percentages as decimals, so 0.9, 0.95, and 0.99. Now, when we are trying to interpret a confidence interval, we are saying that we are blank percent confident that the population, choose the parameter, is between our lower bound and upper bound. In other words, we are blank percent confident that the population, choose the parameter, is between our two values in our confidence interval. Okay. An incorrect interpretation would be that there is 95% chance that the true value of the parameter falls between two numbers because the parameter is fixed. So it either is or isn't in the interval. So there's no probability involved. Another way, 95% of sample data will fall between two values. Again, the interval is about the parameter, not individual data values. And the third one, there is a 95% probability that the parameter lies between these two values. Again, here the parameter is fixed, it's not random. So we want to make sure that we write our interpretation correctly. We are said, for example, 95% confident that the true population proportion is between the lower bound and upper bound. This means that if we repeated this sampling process many times, about 95% of the intervals we create would contain the true parameter. All right, margin of error. So the margin of error, capital E, is a measure of how accurate the point estimate is, and it depends on three factors. The first factor is the level of confidence. So as the level of confidence increases, the margin of error decreases. So higher confidence equals wider interval. So we need to cast a wider net to be more confident. Sample size. As the sample size increases, the margin of error decreases. So larger samples give more precise estimates. And number three, standard deviation of the population. The larger the spread in the population, the wider the interval will be. So more variable populations equals less precise estimates. So the margin of error can be thought of as the give or take portion of the statement. In other words, the mean is blank, give or take blank. So, for example, we could say the height or the average height is 68 inches, give or take 2 inches, means the margin of error is 2 inches. So the margin of error is the maximum error we are willing to accept in the estimation process. E is the maximum likely difference between the observed proportion and the true population proportion. All right, now let's talk about building a confidence interval. So the confidence intervals for mean and proportions are created by taking the point estimate from your sample and adding and subtracting the margin of error. So you have the point estimate plus or minus the margin of error. So if you're asked to find the point estimate and margin of error from a confidence interval, this means that you are given a confidence interval, you can now work backwards. So the point estimate is now going to equal the upper bound plus the lower bound divided by 2, and the margin of error E is going to equal the upper bound minus the lower bound divided by 2. Why does this work? Well, the point estimate is right in the middle of the interval, and the margin of error is half the width of the interval, which that allows us then to create our two formulas for finding the point estimate and margin of error. So let's do an example. Okay, so we're going to be working backwards from a confidence interval. In this problem, we're asked to determine the point estimate for the population proportion and the margin of error for the confidence interval 0.25 and 0.31. So for our point estimate, we are going to take our lower bound and upper bound, add it together, and divide by 2, which gives us the answer 0.28. Before we do our confidence interval, we're going to do our margin of error. Got ahead of myself there. We're going to do our margin of error, which is 0.31 minus 0.25 divided by 2, which gives us 0.03. So then our confidence interval can now be written as 0.28 plus or minus 0.03. Okay, awesome. Why don't you pause and attempt this practice problem, and then return and I will walk through it with you. Okay, hopefully you have attempted the problem. So our answer for this problem, we are given the confidence interval and you're asked to find the value of the point estimate and the margin of error. So you would take your lower bound and upper bound, plug them into our formulas where we add them together and divide by 2 to find the point estimate, and then we subtract them and divide by 2 to find our margin of error. Okay, so then our confidence interval would be 1.416 plus or minus 5.742. Alrighty. Okay, so how to construct a confidence interval for population proportion. So our calculator can construct our confidence intervals for population proportions when we enter in an X and N into our calculator. Okay, so in our calculator, we would go to stats and then over to tests. In the test, we would locate A1 prop Z int. And in this test, we would then enter in our X and N confidence level and then calculate. Okay, and that would then give us our confidence interval. So let's do an example together. So in this example, a researcher wants to estimate the true proportion of all college graduates who smoke. A random sample of 785 college graduates reveals that 144 of them smoke. Construct a 90% confidence interval estimate for the true proportion of college graduates who smoke. A first asks us to verify the assumptions. And remember, previously in our notes here, we stated that we needed to assume that one, the sample size is no more than 5% of the population size, that n times p times 1 minus p is greater than or equal to 10, and our sample is taken from a random sampling. Well, our problem here says that there is a random sample. So now we just need to assume that one, the sample size is no more than 5% of the population size. So the sample size must be less than or equal to 5% or 0.05 of the population size, which is capital N. In solving for N, the population size, must be greater than or equal to 15,700. So 785 has to be less than 5% of the population, which means the population must be 15,700 or greater, which we are assuming that it is. And then n times p times 1 minus p must be greater than or equal to 10. When we enter in our n, which is 785, our p, which is 0.1834, and our 1 minus p, which is 0.8166, we then get our answer to be 117.585, which is greater than 10. So we are good to go. All right. B, we are asked to now calculate the confidence interval. So first, our X is 144. Our N is 785. So that is our sample size. X is the number of successes. So in this case, the number of college graduates who actually smoke, which is 144. And our confidence level is 90%. So we would grab our calculator then to find our confidence interval. So we are now going to locate our confidence interval. So we will now press stat. We'll go over to tests. Then we will go to A, press enter. We'll enter in our X, which is 144, our N, which is 785, and our C, which is 0.9, and press calculate. Okay. And so now we have our confidence interval, we have our population proportion, and we have our N, which is 785. Okay. All right. So what is our interpretation? Well, we are 90% confident that the true proportion of college students who smoke is between 0.1607 and 0.2062. Let's do another one. Pet ownership. So a Gallup poll conducted December 11th through 14th found in 2006 found that 604 of 1,010 Americans own at least one pet. Okay. So we are going to verify the requirements. So the sample size is no more than 5% of the population size. And n times p times 1 minus p is greater than or equal to 10. So when we take all those values and multiply them together, we get 242.8. So to obtain a point estimate for the population for the proportion of adults who own at least one pet, we need to identify our X and our N. Well, our N here is going to be our sample, and that was the 1,010 Americans. Out of that number, only 604 own at least one pet. So to find P hat, we are going to take X divided by N, which gives us the value 0.598. So for C, we're now asked to construct and interpret a 90% confidence interval for the percentage of Americans who own at least one pet. So we will grab our calculator. We will press stat, go over to tests, go to A. And so now our X is 604. Our N is 1,010. Our C level, confidence level, is 95, so 0.95. And we'll press calculate, giving us the interval 0.5678 and 0.6283, rounding to 4 decimal places. Okay. So our interpretation will be that we are 95% confident that the true percentage of Americans who own at least one pet is between 56.78% and 62.83%. Okay. All right, so now let's pause, and I would like for you to attempt this next practice problem. All right, hopefully you've attempted it. For our problem here, in a survey of 2019 adult Americans aged 18 years or older, 1,252 stated that they frequently worry about their financial situation. You're asked first to verify the requirements. So the sample size, again, is no more than 5% of the population size. And N times P times 1 minus P is greater than or equal to 10, which gives us a value of 294.9. You are next asked to obtain a point estimate for the proportion of adults who worry about their financial situation. So your X and N are given to you in your problem. So that's 1,252 for X and 2019 for your N. Dividing those values, you get 0.620. So for C, to obtain a 90% confidence interval for the proportion of adult Americans who frequently worry about their financial situation, you would have to use the 1-prop-Z test in your calculator, giving you the interval 0.6023 and 0.6379. So your interpretation would sound like we are 90% confident that the true proportion of adult Americans who frequent worry about their financial situation is between 60.23% and 63.79%. All right. Objective 3, determine the sample size necessary for estimating a population proportion with a specified margin of error. So, we first need to understand critical values before we can achieve our objective in this part. So, a critical value is a number that separates sample statistics that are likely to occur from those that are unlikely to occur. And below here, I have critical values tables for the 3 major confidence intervals. So for a 90% confidence, we have alpha at 0.1 and alpha divided by 2 at 0.05. For 95% confidence, alpha is 0.05, alpha divided by 2 is 0.025, And then 99% confidence, alpha is 0.01. Alpha divided by 2 would be 0.005. Okay, so why do we have alpha divided by 2? We've looked at alpha before in previous sections where alpha was the area under the curve. But why do we need alpha divided by 2? And this is because in a two-tailed confidence interval, remember we split the area outside of the interval equally between the two tails of the distribution. So if the 90% is in the middle of our distribution, we still have our two tails. And while the total area would equal 0.1, each tail individually would be 0.05. Okay. So finding critical values, we are going to construct a 95% confidence interval and get the critical value z's that would separate the middle 95% of the most likely p hats or population proportions from the unlikely ones. And to do that, we are going to use the inverse norm. So to find those critical values, we are going to take the inverse norm of 0.025 for the 95% confidence interval. Okay. So when we take the inverse norm of 0.025, we're going to get negative 1.96. And then by symmetry, due to the normal distribution where your mean is 0, 1.96 would be the other z-score that will separate the middle 95% from the two tails on both sides that total a 0.05 area. Okay. All right. So the sample size required to obtain a 1 minus a times 100% confidence interval for P with a margin error E expressed as a decimal is given by the following two formulas. Okay, both of these formulas are provided to you on your formula chart. So if we know P hats, the population proportion, is a prior estimate of P, then we would use this formula right here. And if a prior estimate of P is unavailable, so it's not given to us, we would use this formula right here. Okay. If this does not result in a whole number, either one of these, we need to make sure that we round up to the next highest whole number. Okay. We always want to round up and never down because we'd rather have a slightly larger sample than needed rather than too small. Okay. So let's look at this example. A social worker wants to know the proportion of the U.S. population over age 16 who provide elder care, so unpaid care for someone with a condition related to aging, to others. What size sample should be obtained if the social worker wants an estimate within 3 percentage points of the true proportion with 95% confidence if A, the social worker uses the 2015 estimate from the American Time Use Survey of 16%. So now they're using the percentage 16% as the population proportion for this sample size. So P hat would be 0.16. Okay. So since P hat is given to us as an estimate for P, we are going to use our first equation for finding the sample size for a population proportion. We know what P hat is. We know what 1 minus P hat is because we know what P hat is. And then Z alpha divided by 2. So we would take our 95% confidence, which would mean alpha is 0.05. So 0.05 divided by 2 would be the 0.025 that we previously found. And then we'll find the z-score for that area, which gives us a z-score of 1.96. Okay. We would square that divided by E, and E here is our margin of error. Okay, so we are estimating 3 percentage points of the true proportion with 95% confidence. So 0.03 would be our margin of error from this 3 percentage points. So 3% is written as 0.03, which gives us an answer of 573.68. But again, we'll need to round up. So N here is 574. Okay. So this is the size for the population that this researcher would need to obtain if the social worker wants an estimate within 3 percentage points of the true proportion with a 95% confidence. So now for B, we are going to take that the social worker does not use any prior estimates. Okay. So we know that the margin of error is 3 percentage points. So that is 0.03. We know that the confidence level is 95%, which means alpha is 0.05. So alpha divided by 2 would be 0.025. So to find the inverse norm of alpha divided by 2, we would substitute in either 0.025 or 0.975, depending on, again, how you look at the area. And we would get negative 1.96 or 1.96, again, depending on which one you do. So we would then use our second formula where we don't know our point estimate, and we would substitute in our values. So z alpha divided by 2 and E and square it, giving us 1067.11. Rounded up would give us 1068. Okay. All right. Now it's your turn. So I'd like for you to pause and attempt this problem using the information that we just walked through together. All right, welcome back. So for our first practice here, our school administrator is concerned about the amount of credit card debt that college students have. She wishes to conduct a poll to estimate the percentage of full-time college students who have credit card debt of $2,000 or more. What size sample should be obtained if she wishes the estimate to be within 2.5 percentage points with 94% confidence? We are going to look at it where there are no prior estimates that are used and where a prior estimate is used, where a pilot study indicates that the percentage is 34%. So for the first one, A, no prior estimates, you would be using the second equation where your margin of error is 2.5 percentage points, so that's 0.025. Your C level is 94%, so that's your confidence level. So that means alpha is 0.06, so alpha divided by 2 would be 0.03. Depending on how you use your error under the curve, you can use 0.03 or 0.97 to get your z-score. You will then enter either one of those values into your formula, giving you 1,413.76, rounded up 1,414. Now for B, you are given a prior estimate. So you can utilize that percentage, which is 34. So P hat here would be 34% or 0.34. Plugging in that value into our first equation for finding the estimate for the sample size, we would plug in P hat, 1 minus P hat, Z alpha divided by 2, which we found in A, divided by our margin of error E, which is 2.5 percentage points, getting us 1,268.99. Rounded up would give us 1,269. Okay. And that concludes section 9.1.